Okay, the first thing I'm going to do is I put 2 problems on the board. I'm going to give you another 5 minutes or so to try and figure that out, and then we're going to do those together. Examples. This is a review of the last thing that we were doing on Wednesday. This is basically the last topic in chapter 5. Don't forget to look on your Delta Math. There is homeworks there, and there is going to be a quiz posted. In order to make life easier for you, I've made the due date for everything the end of the term. That doesn't mean you shouldn't do it now. It means just that you have, if you don't have time to do it and you want to do it a little later, you will get full credit for doing as long as you're doing the homework and the quizzes on Delta Math. Now, I did also notice that some of the people, I don't know if you didn't realize, aside from the midterm that's on Blackboard, there was the midterm review, which I'm counting as a quiz. So if you haven't done it as yet, make sure to go back, look in the tests and quizzes section on Blackboard, and you will see the test there. And if you'll do it, especially if you do better on that than you did on the midterm, I'll add points. When I figure out your average, I'll add that as extra credit to your midterm. So make sure you get all those. There's a lot to do, but we're getting closer to the end of the term, and I really want to make sure we finish all the material in good time. So both of these questions have to do with dividing polynomials. The first one is a question where we have a polynomial divided by a monomial. The second one, we have a polynomial divided by a polynomial. And what we said is when we have a polynomial divided by a monomial, what we have to do is just rewrite the example, putting each term of the monomial on top of the polynomial on top of the monomial. In other words, rewrite this as 8y to the 5th over the 4y third plus the 10y third over 4y third minus 6y over 4y third. We're going to take each of the terms on the top and divide it by the monomial 4y third. And I'm going to do that by simplifying each fraction. Okay, so here in this first fraction, looking at the coefficients, the numbers, I have an 8 on top and a 4 on the bottom. I can divide both of the top and the bottom by 4. So I'll be left with just a 2 on the top. And the letters, remember you always cross out the lower exponent. So the y to the third is the one with the lower exponent. And you subtract that exponent from the higher one. So 5 minus 3 is 2. So we get a y to the 2, or a y squared. Should write this is 2y squared on the top. Notice the y squared is on top because the higher exponent is on the top. Now everything canceled out from the bottom. So really on the bottom, I'm going to write it over here. On the bottom, what we're getting, so we're getting the 2y squared on the top and a 1 on the bottom. We then go to our second fraction. So we have a 10 on the top and a 4 on the bottom. We can divide both the 10 and the 4 by 2. So we'll be left with 5 on the top and 2 on the bottom. And with the exponent, with the y's, we both have the same exponent. So we can cross them both out. They're both canceled out. When you have the exact same exponent, in other words, y cubed divided by y cubed just cancels out. You're just left with 1. So for the second fraction, we're left with a 5 over a 2. No y's left. Now we're going to our last fraction. So we have a 6 on top and a 4 on the bottom. So we can divide both of those by 2, which will give me 3 on the top and 2 on the bottom, because dividing by 2. And here I see I have a y, which is a y1 on top and a y3 on the bottom. Now that means I cancel out the one with the lower exponent, which is the plain y, and I do 3 minus 1, which gives me 2. So I get a y squared. Now this y squared happens to be on the bottom because that's where in this fraction the higher exponent was. So that last fraction becomes the 3 on the top and 2y squared on the bottom. When you're left with a 1 in the denominator, in the bottom, you don't have to write it out. You could just have written this as 2y squared. If you're left with a 1 in the numerator, you must put that in. You must put it in because you have to be careful to keep what's in the denominator, what's in the bottom, and the bottom, what's in the top, in the top. The only thing you can neglect to put in is that 1 in the bottom. So we could have written this answer as 2y squared plus 5 over 2 minus 3 over 2y squared. And that would be your answer in simplest form. That's what you do when you divide we're not reducing, we're dividing a polynomial by a monomial. Okay. So now let's go to this second question. In this question, we have 4 terms, 2y cubed minus 9y squared minus 17y plus 39, divided by a binomial 2y minus 3. And if you recall what we did on Wednesday, we knew we had to do this as a long division problem. We rewrite this with a 2y minus 3 on the outside, write our division sign, and we put the 2y to the third minus 9y squared minus 17y plus 39 on the inside. The outside number is called the divisor. The inside number is called the dividend. That's so important to know that. The answer, and that's important to know, is the quotient. When you say find the quotient, it means find the answer when you're dividing. Okay, let me just move this up a little bit so it's not in the way. The first thing we have to do when we are dividing by a binomial is to make sure everything is in the correct order. Is this in descending order? Well, my first term is a y to the third, which means my next term should be a y squared, which it is. The next term should be a y, which it is, and the last term should be a plain number. This is in correct order. Also, make sure there's nothing missing. That if there's a term missing, you put a 0 in place of it to keep it as a space maintainer, to keep the space. Like, in other words, if there would have been no y squared, if it would have been just this, I would have put a 0y squared just to keep the space for the y squared. Then what we do is we take our first term, which in this case is 2y, and divide it into the first term. So the 2 into the 2 cancels out, and the y into the y cubed gives me y squared. And I put that right on top. I just divide, not by the whole binomial, but just by the easier part, the first part of it. 2y into 2y cubed. It doesn't matter where you put it on top, as long as it's just on top. You put it on top. And then what you do, let me just remind you, so we did divide. The next thing you do is you multiply using symbols. What do we multiply? We multiply what we just put on top by the binomial. So we do y squared times 2y, which gives me 2y to the third. And y squared times -3, which is -3y squared. Notice when we're multiplying by the whole thing. Even though we didn't divide by the whole thing, when we multiply, we make sure to use the whole thing. And the next step is to subtract, just using symbols. Now, since this is subtraction with variables, this is algebraic subtraction, we're going to do it the way we do subtraction in algebra, where we change the sign of the second number and then we add. So this 2y cubed is a positive, we're going to make that a negative. And this -3y is obviously negative, so I'm going to make that a positive. And then I'm going to combine 2y cubed and -2y cancels out. You'll see when we're doing this, the first pair will cancel out. You're left with something from the second pair. The second pair has a -9y squared plus a 3y squared, which gives me -6y squared. You're going to have to be neat about this, and you're going to have to be careful with your signs. After you do the subtraction, you bring down your next number or your next term. Well, the next thing I bring to see is -17y. So I bring that down. And now I go back to step number 1. I take the first term of my divisor and divide it into the first term of this new expression here. So I do 2 into -6 gives me -3. And y into y squared. Remember, when we're dividing the variables, we're subtracting exponents. 2 minus 1 is 1. So that gives me a -3y. 2y into -3y squared gives me 2y into -6y squared gives me -3y. Again, first term divided into first term. So now I'm at step 2. I take what I just put on top, which is the -3y, and multiply the binomial by that. So -3y times 2y is -6y squared. And -3y times -3 gives me plus 9y. And again now, I've multiplied, so now I have to subtract, which means I'm changing my sign. So this is going to become a plus, and this one is going to become a minus. And then I'll have -6y squared plus 6y squared, which will cancel out. And now I have a -17y minus a 9y, which together gives me -26y. And I bring down the next number, which is plus 39. And I start with step 1 again. 2y into -26y. So the 2 into the -26 gives me -13. The y's cancel out. I take what I just put on top, the -13, and multiply by it. -13 times 2y is -26y. Negative 13 times negative 3 is plus 39. And now I subtract. And I subtract by changing the signs. So this negative, remember, it's always a battle sign. So the negative 26 is becoming a positive 26. The positive 39 is becoming a negative 39. And when I add them, the negative 26 and the y plus the 26y cancel out. But so does the positive 39 and the negative 39 cancel out. And it turns out that I'm finished. There's no remainder. If there had been a number here, I would have taken that number and put it over the divisor, but there was no number. My answer is, this is my quotient, y squared minus 3y minus 13. And notice we put things, we're very careful about, you've got to be neat about this. Because if you're not being neat, you're not going to see what's the next thing to come down. So be careful about doing things very neatly. Okay, I'm going to put another question on the board. I'm going to do it as a multiple choice example. And I'm taking this off of previous final. And let's see if you could do this one on your own. I'm going to erase the top one. I'll leave the bottom one there so you can follow the steps. And while you're going to be doing that, I will take attendance. It says, find the quotient and remainder when the first polynomial is divided by the second. So the first polynomial is x squared plus 12x plus 25. And the second polynomial, which is what you're dividing by, is x plus 9. And here are your choices. A, x plus 3, comma, negative 2 over x plus 9. Remember, the first is going to be the quotient, the second is going to be the remainder. B is x plus 3 and 1 over x plus 9. C is x plus 4, the remainder of 0. And D, x plus 3 and 2 over x plus 9 as your remainder. Okay, so here's your question. You're dividing your polynomial, your first polynomial by your second. You're finding the quotient and the remainder. Okay, and while you're doing that, I'm going to be taking attendance. I'll just look on the, I won't even have to call it, I'll just look on the participant list. Emma, you're here. Naya, you're here. Iris, you're here. Carly, you're here. Kayla. You're here. Kiana. Oriana.
You said Kiana?
Yeah, I see you're here, Oriana. I'm just looking at the
No, Kiana.
Kiana. Yeah, I have you. I'm looking at the participants, and you're there. Patricia, you're here, and Ruth. Jenna, you're here.
Yes, I'm here.
Yeah.
Morning.
Okay. Let's see. Believe that. And remember, you can put your answer on the chat. A, B, C.
Professor, you didn't say my name.
Yeah, I saw you that you were here. Naya.
Oh.
I did say it.
Alright.
I just sort of just looked at the participant list and just did the attendance from that, so you could concentrate on your work.
Okay,
Thank you. Again, make sure you are up to date on all your homework, your quizzes on Delta Math, and the 2 tests that were posted on Blackboard. You should have 2 marks on Blackboard. One is the test that's on the tests and quizzes section, which is a pre-test for the midterm. It's counted as a quiz. Also, if you do better on that than you did on the midterm, I'll give you extra credit to your midterm. So make sure you do that. Remember, that's when they had 2 chances to do. So if you don't do it well the first time, you might do better the second time. So make sure you do that pre-test. It's in the tests and quizzes section of the Blackboard account for Math 136-006C. Also, there is the midterm, which is in its own section. It's called midterm. It's right, just look at those sections on the left side of the when you open up your Blackboard account. Just look at the different sections that you're given on the left side. Also, I've been posting the recordings of the classes that we've had. So if you have any questions about things that we did previously, you could always go back and look at those previous those recordings of previous classes. Anybody have an answer yet? Give you one more minute. Okay, I think we should start work on this together. This it's a little bit, this is a little bit of a challenging topic. But I'm gonna do one more, we'll review it again on Monday, but this is not, we have to go on with new material after this. I'm erasing this so I can have room to do that new question. Again, since I see we have a polynomial x squared plus 12x plus 25, and to be a trinomial, that we want to divide by x plus 9, because it says quotient. Quotient means divide. So we have to divide by the x plus 9. I have to do that as a long division example by putting the x plus 9 on the outside and the x squared plus 12x plus 25 on the inside. It has to be in descending order, which it is. So I rewrite this as with the x plus 9 on the outside, my division sign, and my x squared plus 12x plus x plus 25 in the inside as the dividend. And then we take our first term, x, and divide it into our first term, x squared. And that x into x squared goes x, because x times x is x squared. After we divide, we multiply by what we just put on top by the whole binomial. So we do x times x is x squared, and x times 9 is 9x. And now I'm going to subtract by changing the sign. So this is going to become a negative because it was originally a positive. And this is going to become a negative as well because it was originally a positive. Again, where there is no sign, it's understood to be positive, so it becomes a negative. And we get x squared minus x squared, which cancels out. And then we get 12x minus 9x, which gives me 3x. And I bring down the next number, which is the 25, and start the process again. X divided into 3x. Well, the x's cancels out, and this is really like a 1 in front of it. 1 into 3 is 3, so we get a plus 3. So notice I can right away tell you that choice C is no good. But the others all say x plus 3, so we have to find out, go further. We take what we just put on top, which is a 3, and multiply it. 3 times x is 3x. 3 times 9 is 27. And after I multiply, I now subtract. I first change the sign, so this is becoming a minus, and this is also becoming a minus. So I get 3x minus 3x, which cancels out. 25 minus 27 is minus 2. I can't go any further. There's nothing more to bring down. My remainder is negative 2. In other words, this becomes negative 2 over x plus 9. And if you notice, that happened to be choice A. Anybody pick choice A? Nobody sent me a chat. But that would have been your correct answer, choice A. Because you got x plus 3 with negative 2 over x plus 9 as your remainder. Notice you could put the minus in front of the fraction, or you could put it in the numerator. It doesn't make a difference. Okay, so let's go on to chapter 6 and start talking about what chapter 6 is all about. And basically, the most important thing that we're going to be doing in chapter 6 is finding what we call square roots. I'm sure you've seen the symbol before. It's called the radical sign. And when you see that sign, it's telling you that you want to take the square root. In other words, if you do radical 25, then I'm asking you, what is the square root of 25? Now, the square root means the number that you multiply by itself to get 25. And if you think about it, there really could be two choices. There could be positive 5. 5 times 5 is 25. But negative 5 also works because negative 5 times negative 5 is also 25. But to avoid confusion, whenever I use this radical sign, it always indicates what we call the principal square root or the positive square root. So this square root, this radical 25, answer is 5. If I put a negative in front of it, negative radical 25, that will give us negative 5. In other words, the radical itself is always going to be positive. I'm going to erase this now. Now you can use your calculator to find the square root. Usually the square root button, not in all calculators, if you don't find it, then you'll have to send me a picture of your calculator and I'll find it for you. Usually there'll be a button on your calculator that says x squared, and right above it, there'll be the radical sign. So if that's how your calculator works, what you'd have to first do is press what we call the second button, which is usually near the top of your calculators. I can't give you specific instructions because I don't know exactly which calculator you're using, but this is pretty general for all calculators. You press your second button, you press your x squared button, and what will pop up will be this radical sign. And you'll put in your number. Let's say your number is 25. And then you press enter, and your answer will be over here. Enter or equal, and your answer will come out at the end. Remember, it'll show you actually something that looks like square root of 25. Because if you have a 2-line calculator, it shows you what you entered and it shows you your answer as well. So make sure you know how to do radicals or square roots on your calculator. Now, 25 happens to be something called a perfect square. It happens to be a number that has a square root. The square root of 25 is 5 because 5 times 5 is 25. Again, if you want to do the square root, though, of, let's say, something like this, the square root of 72. 72 is not a perfect square. There's no number, exact number, that works, that when you multiply by itself, it will give you 72. Yes, 8 times 9 will give you 72, but there's no number that multiplied by itself will give you 72. But if I go to my calculator, and I put in the square root of 72, I will get a very long decimal. I'm not gonna go all the way. You could, no, I'm gonna go to, let's say, 4 decimal places. If I go to 4 decimal places, I do 8.45. I'm sorry, 4.85. Now the next number is a 2, but the number after the 2 is an 8, so I round this up. I'm going to, this is in, it's not exact. There is no exact number that will give you the square root of 72. The square root of 72 is called an irrational number. It doesn't have an exact square root. That's what irrational means. A rational number will have an exact square root. The square root of 25 is rational because it has the exact, it's equal to 5. But the square root of 72 is irrational because it gives you, if you had 100 spaces on your calculator, it would fill up all 100 spaces. If you had 1,000 spaces, it would keep going on. It's a non-repeating, non-ending decimal. That's what we call an irrational number. So obviously, when we have rational numbers, when we have square roots and they come out to be nice even numbers, we know how to deal with them. The question is, what do we do when we have irrational numbers? So that's one of the questions we're going to be answering today. But before we go there, I want to make another couple of comments. Number one, when you're doing the square root of a number, you cannot have in a real number, you can't have there can't be any negative inside your square root. We're going to talk about a little later what happens if there is a negative in a square root. There's a special number system that we can deal with that comes in a little bit later in this chapter, but for the normal numbers that we use on a regular basis, which is called the real number system, the numbers that we see on the graph, all those are real numbers. You cannot do something like the square root of negative 25. Well, let's think why. The square root means a number that when you multiply by itself. Now, this answer couldn't be 5 because 5 times 5 gives you positive 25. It can't be negative 5 either because negative 5 times negative 5 would also give you positive 25. In other words, there's no regular real number that will give you, when you multiply by itself, will give you a negative answer. Because if it's positive and you multiply by itself, it'll be positive. And if it's negative and you multiply by itself, it will also be positive. So therefore, this is not a real number. We're going to, as I said, a little later in the chapter, talk about a special number system where we could do something like that, but it's not the regular numbers that we use on an everyday basis. So that's number one. The numbers inside our radicals, our square roots, have to be positive. We can do the square root of 0 because the square root of 0 is 0. If the number is what we call a perfect square, like the square root of 25 is rational, the square root of 36 is 6, it's rational, the square root of 144 happens to be 12. These are all rational numbers. And of course, if you stuck them into your calculator with your square root button, you would come out. You put in square root of 144, you'll get 12. But if you do something like the square root, just the square root of 2, and you stick it into your calculator, you're going to see you're going to get this long decimal. It'll fill up your whole calculator. As many spaces as your calculator has, This will fill it up. That is irrational. 2 is not a perfect square. There's no number that we know, a regular number that when you multiply by itself will give you 2. So this one is rational. And this is irrational. Okay. Dealing with rational numbers is easy. Just stick it in your calculator. We're going to talk a little bit as to what to do with irrational numbers in a few minutes. But before I get to that, I keep saying I'll get to it. I just want to tell you one other use of this radical sign. We use it, and for this course, mostly that's what we're going to use it for. We're going to use it for what we call square roots, a number times itself. But you could have something like called a cube root or a third root, a fourth root, a fifth root, a sixth root. What does, let's say, a cube root or a third root mean? Let's say I wrote something like this. In this little check mark, inside the check mark, if there's a number there, that number is what we call the index. And it indicates how many times you're going to be multiplying the number by to get the number inside. This is read the third root, or sometimes the term is the cube root of -8. What I'm looking for in that case is a number multiplied 3 times that'll give you -8. Now, when you have a cube root, you actually could have a negative in the number, because if you notice, if you took -2, you do -2 times -2 is +4, and +4 times -2 is -8. So the cube root of -8 happens to be -2. It's the number that you multiply 3 times in order to get the number inside. -8 is what we call a perfect cube, because it's -2 times -2 times -2. Again, anytime your index is odd, that means you're multiplying the number by itself an odd number of times, you can have a negative. But if your index is even, the number has to be only a positive number, because if you multiply a number by itself an even number of times, the answer has to be positive. Okay, what does this mean? Let's say I did something like this. The cube root of 64. This means I'm looking for a number that multiplies by itself 3 times and will give me 64. Now, don't make the mistake and think it's 8. I know the square root of 64 is 8, because 8 times 8 is 64. But when I see this index 3, it means I want the number to be multiplied 3 times. That happens to be the number 4. You really should know that the cube root of 8 is 2. The cube root of 27 is 3. The cube root of 64 is 4. And the cube root of 125 happens to be 5. This list of basically, we're not going to be asked a lot of questions about cube roots. Again, the questions are mostly going to be about square roots. So you should know, at least recognize these 4 numbers as what we call perfect cubes, and know that you can do their cube root. There is a way of doing cube root on your calculator. Again, it differs with each calculator, so I'm not going to go into it. You're not going to have a lot of questions that have to do with cube roots. All right, so let's go back now that we've mentioned using this radical sign for other types of roots. Let's go back to our study of square roots. Again, when we have this radical sign with no number indicated as an index, there's no number inside that little check mark. That's what we call a square root. Actually, the index, there is an index. The index is 2. Because when we're using it, we want, how many times are we multiplying the number to get what's inside? And the answer is 2. We're multiplying a number by itself to get the number inside. So if no index is indicated, if there's no little number in that check mark, then you know that the index is 2. You're talking about a square root. And again, we mentioned how to find the square roots on our calculators. What we want to talk about now is what happens if we want to simplify a radical, a square root. So let's say I gave you the square root of 50. Now, 50 is not a perfect square. 49 is, because 7 times 7 is 49. But 50 isn't. There's no number that you multiply by itself to get 50. But if you think about it, 50 really could be broken up into 25 and 2. 25 times 2 will give you 50. But there are other ways of breaking up the 50. The reason I picked it to pick up this way is because 25 is a perfect square. Now you're going to recognize, you should recognize the numbers 1 through 12. They're perfect squares. In other words, if I gave you 81, you should know that the square root of 81 is 9. You should know those. Those are, if you don't, make yourself a list. 1, 2 squared is 4, 3 squared is 9. Make a list and make sure you're familiar with them. Okay, so we take this 50 that breaks up into 25 and 2, and we separate it into the square root of 25 times the square root of 2. And then I can take the square root of 25, that's a perfect square, so I can just write it as 5. And my answer then becomes 5 square root of 2, or 5 radical 2. This is what's called simplifying the radical. Why is it simplifying it? Because when even though we still have numbers left, the number inside the radical that we're dealing with is going to be a much smaller number. The harder number to deal with is the number that's the square root, the irrational part. So let's make that number as simple as possible. Let's see if we can do some more examples. So let's see if you could simplify this number. Suppose I gave you the square root of 12. Now, remember, 12 is not a perfect square. So we want to break up the number. I'm going to do a few of these together with you. We're going to break this up into 2 numbers. One of which has to be a perfect square. Now, sometimes you're going to have more than one choice. If you have more than one choice, pick the larger perfect square. Again, you want you're not gonna know that, either you're gonna recognize that 12 is not a perfect square, you should. If you don't, if you stick it into your calculator, you'll see right away, because if you try to do square root of 12, it'll come out to be a long decimal. But we know that 12 could be broken up into 4 and 3. 4 times 3 is 12. Notice I always put the perfect square first, because that's what's going to come out of the radical. The square root of 4 happens to be 2, so this simplifies into 2 radical 3. Let's say I had the square root of 700. What can I break up the square root of 700 into? Well, we can break that up into 100 times 7. And the square root of 100 is 10. So the answer to this one becomes 10 times the square root of 7, or 10 radical 7. So the whole process involves breaking up your square root into 2 numbers. One has to be a perfect square. Let's say I gave you the square root of 48. Now, 48 is not so simple. Let's make a list of numbers that multiply to 48 and see if we can come up with any numbers that are perfect squares. Well, 2 times 24. That's no good because neither 2 nor 24 is a perfect square. 3 times 16. Well, that's good because 16 is a perfect square. What else can, let's see if we've got the best one. We could have done 4 times 12, and the 4 would have been a perfect square, but I still would have picked this one. So far, this is the better choice because here the perfect square is larger than here. 5 doesn't work. 6, we could do 6 times 8, but neither of those are perfect squares. And 6, I think that pretty much takes all the possibilities of multiplying 2 numbers to get 48. Notice where you have 2 cases where one of the numbers is a perfect square. This number and this one didn't work at all because neither 2 nor 24 was a perfect square. Neither 6 nor 8 was a perfect square. We couldn't take it out of the radical. But in this one, 3 times 16, 16 is a perfect square. And 4 times 12, 4 is a perfect square. They both have perfect squares. I picked the one that's bigger. So I'm going to rewrite this as the square root of 16 times the square root of 3. Remember, I always put the perfect square one first. And it doesn't matter if you write it 3 times 16 or 16 times 3, it's still 48. And this becomes then 4 radical 3. Okay. Now, what happens if you have x's or any variable inside your radical? So let's talk about that, and then we'll go one step further. When you're dealing with radicals and variables, and it doesn't matter what your index is. If you have an index, and every radical will have an index, even if it's not written in its index, then its index will be 2. What you'll do is you'll take the exponent of the variable and divide it by the index. 10 divided by 5 is 2. this would give you x squared. If I gave you the cube root of x 6, y 18, for example. Again, my index is 3. I'm going to take each of the exponents and divide them by 3. So this will be x squared, y 6. And if I give you something like the square root of x to the 16, even though no index is written in here, since it's a regular square root, we know the index is 2. So I take the 16 divided by 2, and that gives me x to the 8. So in a way, dealing with the variables, dealing with the letters and exponents is almost easier than with the regular numbers, because you don't have to find square roots, you just have to divide it by a simple number. You divide the exponent by the index. Again, if no index is written in, the index is understood to be 2. Now that all works very well if you have an even exponent. But what if I had an odd exponent? What if I had x to the 9 inside a radical sign? Now I'm in a little bit of a pickle. 9 divided by, here the index is 2. 9 divided by 2 is not good, comes out to 4.5. I don't want an exponent to be 4.5. I want whole numbers as exponents. What does it mean, x to the 4.5? We'll talk about it a little bit later, but really it doesn't sort of make sense. X to the 9 I know means multiply x by itself 9 times. What does x to the 4.5 mean? Multiply x by itself 4.5 times? That just doesn't make sense. So we want to stick with exponents that are whole numbers. And if we're doing radicals, we know that we have to take the exponent and divide it by the index. Again, this is an index of 2. So we have to do something similar to what we did before when we simplified our radicals. Break up this into 2 pieces. One piece will be a perfect square and one piece not. Now that's going to be very easy to decide what to do, because if it's an even number, it's a perfect square, so you have no problem. And if it's an odd number, as in this case, what you're going to do is you're going to subtract 1 from it. You're going to rewrite this as x to the 8 times. In other words, we're going to break up the x to the 9 to x to the 8 and x. How does that help us? Because the square root of x to this is a perfect square. It has an even exponent. Remember, when you're dealing with variables, if the exponent is even, it's a perfect square. If it's odd, it's not, and it has to be separated. So we take the x to the 8, take the 8 divided by 2, and we get x to the 4th. And this gives us x to the 4th times x. So really, we're now in the position to simplify our radicals as much as possible, because if we have numbers, we can break up the numbers. If we have letters, if we have variables, we know how to do that as well. So let's see if we can try something like this. Suppose I want to simplify the square root of 20 x to the fifth y to the fifth. Okay, I'm gonna do one and then I'm gonna give you one to try. Okay. Remember, it says simplify, so we know we're gonna break it up into our two radicals. The first, we'll put in the first radical all the perfect squares, all the things that we can take the square root of. And everything left over, we're gonna put in the second radical. And we're gonna do it each piece by piece. First, we take 20. Now remember, what does, we can have 1 times 20. Well, neither of those is a perfect square. 2 times 10, neither of those is a perfect square. 3 doesn't work. 4 times 5, that works. And I don't think there are any other choices. So I'm going to break up this 20 into 4 times 5. And I'm going to put the 4 in the first radical and the 5 in the second radical because the perfect squares go in the first radical. Then we go to the letters. The first letter we see is an x to the fifth. Its exponent is odd, which means I have to take one away from it, which will give me x to the fourth, and put a plain x in the second. So x to the fourth times x will be x to the fifth, and the x to the fourth is a perfect square because its exponent is even. Then we go to the y fourth. Notice I'm not taking square roots, I'm just separating. That's step 1. Y to the fourth has a even exponent, so that's a perfect square. So it totally goes into that first radical. Now, in this first radical, what I have is a perfect square. So I can take its square root. The square root of 4 is 2. And the exponents I divide by 2, I get x squared and y squared. And what's left inside the radical is 5x. So the answer in simplest form is 2x squared y squared times the square root of 5x. Notice I don't put a times sign, but everything here is being multiplied. And the reason it's considered simplest form is because what we have in our radical is smaller than what we started out with. We want as small as possible a radical as we can get. Okay, let's see if you can do this one. Let's see, you have 72 x 8 y 7. Let's see if you can simplify that. Okay, let's see if we can work on this together. We want to simplify it, so we're going to break it up into our two radicals. Now, the 72 is going to be the harder part to deal with. So let's do what we've been doing before. We have 1 times 72. Then we have 2 times 36. And actually, I'm going to start right there because 36 is a perfect square. This is, try and make yourself a list, and if you have a calculator, you just divide it by 1, well, obviously you don't have to divide by 2, by 3, by 4. See if any of those numbers give you a perfect square. So I'm going to break up the 72 into 36 and 2. Now I'm going to deal with the variables. X8 is even, the exponent is even. I put it totally in the first radical because it's a perfect square. Y7 though has to be broken up because it's odd. I'm going to take 1 away from it. I'll get y to the 6 and put that in the first. And in my second radical, I'll get just a plain y. And now I can take the square root of everything that's in my first radical. Square root of 36 is 6. Remember, the exponents you're dividing by 2. So it's x fourth, y to the third, and then we have radical 2y. So that's what we call simplifying radicals. I'm just going to go one step further. One of the main reasons we want to simplify radicals, aside from being able to compare answers, if you have an answer in one format and I have it in another format, we might not know that we have the same answers. If we simplify our answers, then we'll all come out with the same format and it'll be easier to compare answers. But there's even another reason why it's so important to be able to simplify radicals. And that's because of the rule for adding and subtracting of radicals. The rules for adding and subtracting in radicals is just like the rule for adding and subtracting letters. You know that you can only add or subtract, let's call the word combine, like terms. In other words, if I have a 5x plus a 7x, I can combine those to 12x. Whereas if I have a 5x plus a 7x squared, they can't be combined anymore simply because they are not like terms. Let's see how this works with radicals. If I have something like 5 radical 3 plus 7 radical 3, these are like radicals. Why are they like radicals? Because the radical part, not the number in front, but the part that's inside the square root, they are identical. Therefore, just like these are like x's. It's like a 5x and a 7x. You're going to add just the numbers in front, and you're going to get 12 radical 3. If you have something like 5 radical 3 plus 7 radical 4, well, that was a radical 4, you could probably simplify. That's not. These are not like radicals. This is a 3 inside the radical. This is a 5. These cannot be combined. They are not like radicals. That's why it's so important to be able to simplify radicals, because sometimes things that don't look alike, after you simplify them, actually do turn out to be like radicals. So let's say I had an example like this. 2 radical 75 minus radical 48 plus radical 12. And I'm told to simplify. I want to simplify that. Now, when I look at it initially, it looks like they're not like radicals. Looks like I can't do anything with it. Because if they're different numbers inside the radicals, I cannot add them. I can't go like this and do 3 plus 5 and oh, this is radical 8. It doesn't work that way. You can only add or subtract radicals that have the same exact thing inside their square root. So what are we going to do with this? What we're going to do is first try and simplify each of the radicals. And after everything is simplified, we're going to see if maybe some things will match. Maybe there will be some like radicals. So first I take this 75. So the 75 I know could be broken up into 25 and 3. Notice 25 is a perfect square. And 25 times 3 is 75. Now don't forget there was a 2 here in front. I can now take the square root of the 25, which will give me 5. And now I have, in front of the radical, I have a 2 and a 5 times radical 3. Now, what do you think I should do with these 2 and the 5? Well, there's no sign in between them. So usually that what means when we don't have any sign between 2 letters, it means what we want to do is multiply. So that's exactly what we're going to do here. We're going to take the original 2 and multiply it by the 5 that we've just gotten there. These are both numbers that are not in the radicals, so they could be combined. 2 times 5 is 10. So this first term becomes, in simplest form, 10 square root of 3, or 10 radical 3. Okay, we then go to the 48. Now we did 48 before. If you remember, we broke 48 into 16 and 3. 16 times 3 will give us 48. And 16 is a perfect square. So the square root of 16 we're going to make 4. Notice the only thing in front of that is a minus, like a -1. So we multiply then -1 times the 4. We get -4 radical 3. And finally, we have the square root of 12. Well, the square root of 12 can be broken up into 4 and 3. Because 4 times 3 is 12. And the square root of 4 that's a perfect square, that's 2. So this becomes plus 2 radical 3. So we first simplify all the radicals as much as we possibly can. And then if you notice, these are all like radicals. So then what I'm going to do is combine the numbers in front. When I'm adding or subtracting radicals, it's just like adding and subtracting of like terms. You just add the numbers in front. 10 minus 4 is 6. 6 plus 2 is 8. So this becomes 8 radical 3 as our final answer. So let's go through the steps again. Simplify your radicals as much as possible. If you end up then with 2 numbers in front of your radical, because there was a number originally in front of it, and now you have this new number in front of it, by simplifying, you just multiply those 2 numbers together. So here we got 10 radical 3 minus 4 radical 3 plus 2 radical 3. And then just think about doing it like 10x minus 4x plus 2x. You add up all the coefficients, the numbers in front. 10 minus 4 is 6, plus 2 is 8, and put it in front of your like radical, the radical that's the same for all of them. If 2 of them were alike and the other one was different, then you could only combine the 2 that are alike. And if you have some numbers in radicals and some numbers without radicals, In other words, if I have 15 plus 2 radical 7, I cannot combine those. Because this 15, don't make the mistake of doing 15 plus 2 and getting 17. These are not like radicals. This is like a 15 plus 2x. You cannot combine them because the only thing you can combine this one would be something that also has a radical 7. Okay, I'm going to give you one to try now on your own. I'm going to make it a multiple choice, and you're going to see if you can come up with the right answer. See if I can find one on a previous test. Okay, here we go. Here's the question. Radical 63 plus radical 18 minus radical 28. Okay, and we want to simplify it, and here are your choices of answers. Radical 53, choice 1. Choice 2 is 7 plus 3 radical 2. Choice C is 3 radical 7 plus radical 2. And choice D is radical 7 plus 3 radical 2. Okay, see if you can simplify it and see if you come up with one of these answers. I'm going to give you a couple of minutes to do this. Remember, if you put an answer on the chat, you get extra credit. Okay, Okay, Kayla gave us one answer. Let's see if Kayla's answer is correct. I'm giving you extra credit, Kayla. Oh, okay, a bunch of other people now have come up with answers. Isis, Ariana, and okay, let's see which one we prefer. So the first thing we're going to have to do is try and simplify each of these radicals. So when we look at the square root of 63, let's see, what do I see 63 multiplying to? Well, 3 times 21 works, but neither of those are a perfect square. 7 times 9 works. I think those are the only two combinations, and obviously this is the good combination. The square root of 63 will break up into the square root of 9 and the square root of 7, which will give us 3 radical 7. Now, that's the 63. Now let's go to the 18. The square root of 18, well, 18 is obviously 9 times 2. So that we can break up into the square root of 9, which is 3 times 2. And finally, we have the square root of 28. And 2 times 14 doesn't work, but 4 times 7 does work. We can break this up into the square root of 4 and the square root of 7, which will become 2 radical 7. So now I've gone and simplified each of my radicals. And I notice the 3 radical 7. Oh, this is supposed to be minus, I'm sorry. Not a plus, this is a minus. I combine the 3 radical 7 minus the 2 radical 7. Remember, I do 3 minus 2 is 1 radical 7, which is just radical 7. And there's nothing to combine this with, so that's a 3 radical 2. And my answer is choice D. Look at how easy it could have been to pick B. It's not 7. The 7 is inside the radical. It's square root of 7 plus 3 radical 2. And these can't be combined because they're not like radicals. Okay, I'm going to end the class here. Does anybody have any questions that they want to ask me?